This can be seen sort of simply in this 1D case. So we start off with a prior, and here it is as a Gaussian. We have some measurement that's the evidence, and here it happens to be tighter. And then we get a posterior, right? And the posterior is narrower, and because it's narrower, it's also going to be taller. And then the prediction step, we just take that posterior, and we do the shift, and we grow the uncertainty again. So far, everything looks like it's behaving really well. So let me give you a quiz. Well, it's not a real quiz. It's like a fake quiz, all right? Suppose this is your prior, okay? Okay, so you see it's this nice white Gaussian lump over here. And then suppose this is your measurement, okay, this nice tight green. Where does the posterior go? Well, first of all, it's got to go somewhere in between, because in Kalman filtering, your mean is a weighted average between the prior's mean and the measurement, okay? So the fact that it's going to go in the middle is okay. But what might bug you is it's got, again, that tight little uncertainty. I got this Gaussian bump here, all right? Now, Gaussians go to 0 really, really fast. So by the time we get out here, it's like incredibly unlikely. But then all of a sudden there's a measurement bump over here, okay? So, you know, what's poor Kalman to do? Well, Kalman has to put them somewhere in the middle because that's all it does. And furthermore, it has to reduce that uncertainty because it's a slave to its model. It really, honest to God, believes that things are distributed by these Gaussians. And if they really were, then that's the correct value to put in. And the question is, does this agree with your intuition? And the short answer should be, I don't think so. Because, Megan, over here, okay? If I've really got a Gaussian lump over here, then the idea that something will now be over here, the probability is so infinitesimally small that what's probably the problem is that our model is wrong. We really should be trying to abandon the model at that point as opposed to doing the integration. And in some sense, that's the part of the message of Kalman filter. You're actually a slave to the model. You really believe it.